Apparent position is referring to the fact that when we view an object in one medium, such as a fish in water, and if we view it from another medium, in this case the air above the water, the object will appear to be at a different location. That's because if you consider a point source on this fish, the light diverges from that point source. And then when it goes from this high index to a lower index medium, the emergent rays will diverge even more. The observer in the air can only see the emergent rays, and those emergent rays appear to be coming from a different location. In this case, they'll see an image of the fish which appears to be closer than where the object really is. Now I've redrawn the diagram so that the light is going from left to right, and we can label some of these distances here. So from the actual object to the interface, we will call L, and from the image to the interface, we call L prime, the image distance. The index of refraction, where the incident rays are located, is N, and the index of refraction, where the image rays are located, is N prime. And these are all related by the equation L over N, so the object distance over the object index of refraction is equal to L prime over N prime, the image distance over the image index of refraction. For our first example, we could say that a fish is located 30 centimeters underwater, and we want to find where the apparent position of the fish is. So if the fish is actually 30 centimeters underwater, we use that as our L. The index of the water is 1.33. And we know the index of air is 1.0. And we're trying to solve for L prime, which would be the apparent position of the fish. So here, 30 over 1.33 is L prime, equal to L prime over 1. And you can solve for L prime and find that the apparent position of the fish is 22.55 centimeters below the surface. So as we expect, it appears to be closer than it actually is. And the same idea comes into play when we talk about the apparent thickness of a material. So if we were to have a block of glass and an observer was to view that block of glass normal to its surface, it would appear to the observer that the glass is thinner than it actually is. And we can use the idea of apparent position to determine the apparent thickness. To do that, I like to imagine that there's an object or maybe a small speck of dust on the back surface of the glass. And light will diverge from that point, and here again it's going from higher to lower index, so it will diverge even more as it goes into the air. And again, these emerging rays appear to be coming from a point that is closer to the surface than the actual back surface is. So the way that I have my drawing here, this piece of glass would only appear to be this thick, because that's where the image of that back speck of dust is located. So if we say that this piece of glass is 5 centimeters thick, and the index is 1.45, we could then calculate the apparent thickness of the glass. And again, we can use L over N equals L prime over N prime. Remember that in this case the N is where the object is originally located, so that's the index of the glass. And the L is the actual object location, so that would be 5 centimeters over 1.45 is equal to L prime, which is the image location we're trying to find, divided by the index where the incident or the emerging image rays are. So for here, N prime is the air, 1.00. And we can solve for L prime to find that the image distance is 3.45 centimeters, and so the apparent thickness of this plate of glass would be 3.5 centimeters instead of the actual 5 centimeters.